Have you ever looked at a towering skyscraper or a huge solar farm and just wondered, how does that thing not get blown over in a massive storm? Well, it's definitely not magic. It's engineering. Today, we're going to dive into the powerful, invisible force of wind and see how modern science actually tames it. So, here's a strange question for you. What in the world does a destructive tornado have in common with a field of solar panels? I know it sounds like a riddle, right? But the answer connects back to safety, stability, and some pretty brilliant engineering. Let's figure this puzzle out together. All right, first things first, we need to be really clear about something. When we're talking about wind and engineering, we are not talking about a gentle breeze. We're talking about a serious, powerful force of nature that has to be respected. For a lot of structures, especially ones that are up high or out in the open, wind is actually the single most powerful force they'll ever have to deal with. It's this relentless pressure that can push and pull and twist, and if you don't account for it, the results can be, well, catastrophic. So, in the world of structural engineering, you can't fight an enemy you haven't named. We call this force wind load. Let's break down exactly what that means. At its heart, wind load is simply the total force that wind puts on a structure. But, and this is a big but, it's not just a simple uniform push. Oh no, it's way more complex and, honestly, kind of fascinating. Wind attacks a structure in a few different ways. We can really boil wind load down into two main troublemakers. First, you've got lateral force. The best way to think of this is like a giant sideways shove that's trying to knock the structure over. But then you've got uplift force. This one's even wilder. It's an upward pull that can literally try to rip a building right off its foundations. Engineers have to design for both of these at the same time. Okay, so how do engineers actually do it? This isn't just guesswork or, just building things extra tick and hoping for the best. They use a very precise rulebook to turn the total chaos of wind into cold, hard calculations. For engineers in India, that guide is IS 875 Part 3. This design code is the official playbook. It gives them a standardized way to calculate and prepare for wind's forces, making sure every single structure is held to the same high safety standards. Now, look at this number, 180 kilometers per hour. While normal wind speeds might be much lower, engineers use what's called a factored wind speed, like this, for their designs. It basically represents an extreme, worst-case scenario. This lets them build in a huge margin of safety by planning for conditions that are way worse than typical. And it's not just one number. The code makes engineers look at four key factors. First is the basic wind speed, which is different depending on where you are geographically. Then there's terrain category, because wind behaves very differently in a crowded city versus a wide-open field. Structure height is a huge one, since wind gets faster the higher up you go. And finally, topography. A building on top of a hill is going to face way stronger winds than one in a valley. All four of these change the final math. So, that's the theory. But let's see how this all comes together in the real world. How do we actually turn these numbers into structures that can stand up to the wind? Let's circle back to our solar panel. It's the perfect example. It's out in the open, it's raised off the ground, it's totally exposed. That means every single component, from the steel frame to the bracing to the anchors in the ground, has to be designed to fight both that sideways push and that upward pull we talked about. The choice of material is absolutely critical. Engineers will often go for something like high-strength, corrosion-resistant steel, like hot-dip galvanized iron, or HDGI. It's not just strong enough to handle the load, it's also tough enough to resist rust and decay from being exposed to the elements 24/7. And this is where modern tech really comes in handy. Before a single piece of steel is ever cut, engineers use powerful software like STAAD.Pro. They build virtual models of their designs, and then they simulate everything. They basically throw digital hurricanes at them. This lets them find and fix any weak spots long before construction even starts. So we've gone through the forces, the rules, and the tools, but why is all of this so incredibly important? Well, the answer really comes down to three huge benefits. Following this super detailed process ensures public safety, first and foremost. It also achieves material economy. You're using exactly the right amount of material, not too much, not too little. And finally, it guarantees that the whole system is going to be durable enough to last for decades. This quote really says it all, doesn't it? Properly accounting for wind load isn't just about following some rules in a book. It is the very definition of responsible engineering. It's the promise that the structures we build are safe, they're efficient, and they are built to last. So, I'll leave you with this thought. The next time you feel a really strong gust of wind, just look around you.
Look at the streetlights, the buildings, the bridges. You now know about the invisible battle that's being fought and won by smart design all day, every day. So what will you see differently?